Okay, it's my pleasure to introduce the first speaker of the morning session, Luen-Chau Lee. And Luen-Chau, you ready? Yes. Luen-Chau Lee from Penn State University. Luen-Chau, where's your... What? You going on the... You're already connected, I hope. Yep. Luen-Chau, we've been asked to use this. And put this somewhere where you can hear it, okay? Let's see, like that, I think. Is that good?
Yep.
Okay.
Yep. Okay. So. Let's see, where is the file? The file.
It was on the desktop. What's on that? Oh, I see.
On that USB, yeah.
That would probably be...
Yeah, this one.
There. You need display mode.
Then do full screen mode, right?
Where's full screen mode, people?
No. Okay. Now, first of all, I would like to thank the organizers for the invitation, and it's a pleasure to be here. Time flies, right? I have known Carlos for more than 40 years. So among the first things that I remember Carlos is this fact. So I think several weeks after I started as a grad student at Courant, I noticed that there's a very athletic person who seems to play tennis regularly and always come back to the institute with a tennis racket. So that was before I actually knew Carlos. Okay, now I actually got into integrable systems after making what I call a detour. So by the time I tried to get into the field, Carlos was already about to leave. So, so he's my senior academic brother. Okay, so so today's talk is on infinite periodic band matrices and the periodic total flow. Let me begin with a list of references. So the talk will be based on this paper with the same title as the talk, which has just appeared in June. And so the paper deals with two problems which were left open in the work of Moerbeke and Mumford. So in 1979, and so as I remember, a classmate at Courant, Jun Sir, gave me a copy of the paper. Now, but at that time, it was too difficult for me to read because I did not have a background in algebraic geometry. However, I was led back to this problem through the following two pieces of work. So the first one is a paper by Ben Abdul-Jalil, the integrability of the periodic full Kostant-Toda lattice on the simple Lie algebra. So Ben Abdul-Jalil is actually a descendant of Moerbeke because he was a student. She was a student of Paul Van Henke. Okay, so in this paper of Ben Abdul-Jalil, she makes some conjectures. So he showed that the periodic full Kostant-Toda lattice is integrable for any simple Lie algebra, and then she makes some conjecture that the periodic total flow is also integrable in the banded case. So I got interested in this problem because a friend alerted me to this problem. And so in joint work with Sahu Ni, we solve the conjecture in the case when the Lie algebra is SLNC. So after doing this work, I was wondering I asked the question, if I generalize the banded Kostant-Toda flow, can I relate that to the systems which were discussed in Moerbeke and Mumford? So that was my question. And then it turns out to be the case. Okay, so let me just give one page of historical background. So in the mid-1970s, study of KdV equation with periodic initial data and the periodic total lattice have led to the development of an inverse spectral theory. So in the case of KdV, this inverse spectral theory has to do with the so-called Hughes operator, which is just the one-dimensional Schrödinger operator with a periodic potential. And then in the case of the periodic total lattice, the operator is a second-order periodic difference operator, which I call CAB. And so this CAB is defined by means of a three-term recurrence relation here. So here the coefficients, the AKs and the BKs, are periodic and of period equal to n. Okay, so a lot of people have made contributions to these two theories, and including the list of people here. Okay, so now I'm going to get into the question asked by Moerbeke and Mumford. Okay, so based on the success in the second order case, Moerbeke and Mumford asked the following question. Is there a similar theory for generic periodic difference operators with order bigger than 2? Of course, they noted that corresponding question for differential operators is a very hard problem because for periodic operators, the genus of curves are usually infinite. Okay, so a periodic difference operator with period equal to n can be implemented through an infinite periodic band matrix. So I'm going to denote by capital C the infinite periodic band matrix with period equal to n, with lower bandwidth equal to k and upper bandwidth equal to k prime. So what this means is that Cij, the ij entry of this matrix capital C, is equal to 0 outside the band, defined by means of this inequality here. Okay, so following Moerbeke and Mumford, we will assume throughout following conditions on k and k prime. So I will assume that k and k prime are between 1 and n minus 1, and the sum of k and k prime is smaller than n. Okay, so let me give the simplest example. So this is an example in which the period is equal to 3, so n is equal to 3. Lower bandwidth and upper bandwidth are both equal to 1, so k and k prime equal to 1. So in this case, the matrix, the infinite band matrix, takes the following form. So the A's are on the main diagonal. The B's and the C's are the boundary elements of C. So notice that in the general case, the k, the number k, which is the lower bandwidth, this is also the same as the number of non-zero sub-diagonals. And k prime, the upper bandwidth, is the same as the number of non-zero super-diagonals. So in this case, the C's are on the first super-diagonal, and the B's are on the first sub-diagonal. Okay, so first of all, I'm going to go over the two main results in the work of Moerbeke and Mumford. So before I do that, I need to introduce some notation. So D will denote the greatest common divisor of n and k. D prime will denote the greatest common divisor of n and k prime. So n can be factorized in two ways. So n is n1t times also equal to n1 prime times d prime. So in a similar way, k can be factorized into k1 times d, and k prime is k1 prime times d prime. Okay, so the first result of Moerbeke and Mumford is a one-to-one correspondence between two sets of data. First set of data consists of regular infinite periodic band matrices C of period n with lower bandwidth k, upper bandwidth k prime, modulo conjugation by periodic diagonal matrices of period equal to n. Okay, so the second set of data here consists of curves, which I denote by R, a divisor D on the normalization or desingularization R tilde of R of degree equal to the genus of the normalization. And then we have D plus D prime points on R tilde, two functions H and C on this R tilde subject to several conditions. So the D plus D prime points consist of two sets. So the first set consists of the P's, and the second set consists of the Q's. So these are smooth points on the normalization of R, and they have a definite ordering. And the functions H and C are, essentially these are the coordinate functions on the normalization R tilde, and they have zeros and poles as follows. Okay, so equation 1 gives the divisor structure of the function h. So for example, it has a pole of order n1 at the qi's, and has, these are the zeros, and has poles of order n1 prime at the pi's. Yeah, so this is the divisor structure of the, equation 2 gives the divisor structure of the coordinate function c. And so finally, the final condition is that c raised to the n1 prime times h to the minus k1 prime should take on distinct values at the pi's. And there's a corresponding statement for c raised to the n1 times h to the k1. So these will have distinct values at QIs. So that's the first result. Second result has to do with linear flows on the Jacobi variety of this R tilde, which is the normalization of R. So the linear flows corresponds to isospectral deformations of the infinite band matrix C, given by two types of equations. Okay, so in equation 3, P of WC C to the minus 1 is a polynomial in the three variables. The sigma is the shift operator, is a shift by the period n. In the first type of equation, the plus denotes the upper triangular part of the matrix. In the second type of equations, in equation 3, the bracket plus denotes the projection to the upper part, respect to the Cholesky decomposition. So that means you take the straight upper part, and then you add to it 1/2 the diagonal part. So that's the meaning of bracket plus. Okay, so in that paper, Moerbeke and Mumford also make a preliminary study of the integrability of the second type of flows. And so in particular, they exhibit a Poisson structure respect to which the equations in this formula number 4 are Hamiltonian. So they wrote down the Poisson structure. And furthermore, they show that there exists a family of Hamiltonians that Poisson commute with each other respect to this structure. So in spite of this, there's no proof of the Liouville integrability of the flows. And in fact, even the dimension of the phase spaces is not known from this work. Okay, so now I'm going to just give the goals of this work. For concreteness, we're going to consider the equation in equation number 5, which I'm going to call the periodic total flow. So the name periodic total flow comes from the fact that when the bandwidths are both equal to 1, and the matrix C has 1s on the first superdiagonal, the equation comes from the complex version of the periodic total lattice. So the periodic total lattice is just a system of particles on a circle interacting with an exponential nearest neighbor interaction. Okay, so there are two goals in this work. First goal is to establish the integrability of the periodic total flow. And the second goal is to improve on the dictionary of Moerbeke and Mumford. And so I want to remove the modular conjugation by periodic diagonal matrices of period n restriction. Okay, so the second goal, of course, is intimately related to the first goal and can be achieved if we study the integrability of the periodic total flow very carefully. Okay, so now let me just introduce some notation. So G is just GLNC in this talk with the usual pairing. And H is the Cartan subalgebra consisting of diagonal matrices. Eij is the n by n matrix whose ij entry is equal to 1 and zeros elsewhere. So we have a number of these subalgebras of this G. So n minus and n plus are the unipotent subalgebras. So n minus is just the subalgebra consisting of strictly lower triangular matrices. And then B plus and minus are the corresponding Borel subalgebras. Okay, so the basic decomposition here is that G has a direct sum decomposition into B plus with n minus. So, okay, so I'm going to denote by pi b plus and pi n minus the projection operators relative to this splitting. So for J from 1 to n minus 1, I'm going to introduce these vector subspaces of G. So G super J is just the matrices which is supported in the J super diagonal. And similarly, J to the minus J consists of matrices which are supported on the J subdiagonal. Okay, and then G0, of course, just a Cartan subalgebra. Okay, so now I'm going to introduce a second type of flow, which is a generalization of the one in Penn at the JLU and also in my work with Xiaohu. Okay, so here I don't have other words to pick. So I call this periodic total flow on matrix loops of level k, k prime. So the unknown here is a loop in GLNC, which I call L of C. So L of C is a sum of 3 terms with coefficients L1, L0, and L minus 1. And B of C is given by this formula here. So it's L minus 1, C to the minus 1, plus a lower triangular matrix that comes from projecting L0. Okay, so here, the L0, so you can forget about the notations here. L0 is just a n by n band matrix with lower bandwidth equal to k, upper bandwidth equal to k prime. The L minus 1 is an upper triangular matrix, is only supported on the diagonals from n minus k to n minus 1. So only has possibly non-zero entries on the upper right-hand corner. Similarly for L1, so L1 is the lower triangular. It's a matrix with possibly non-zero entries on the lower left corner. Okay, so there are some special cases. When k and k prime are both equal to 1, and the matrix L0 has 1s on the first super diagonal, then this is the complex periodic total lattice. When k is equal to n minus 1, the k prime is still 1 with 1s on the first super diagonal of L0. and L1 equal to En1. This is the periodic full Kostant-Toda flow introduced by Ben Abdul-Jalil. And then in the work of with Sahu, we consider general K. But we still had K prime equal to 1 with 1s on the first superdiagonal of L0. Okay, so in this sense, this more general case, this is the more general case with a general K prime. Okay, so first of all, I'm going to relate the two kinds of flows. There's one kind of flow for C and another kind of flow for matrix loops, right? So theorem A, first part, and this is actually already in the Moerbeke and Mumford. So if C is an infinite periodic band matrix, then the flow K matrix L of C is of the form given in the previous slide. And then this second part of the theorem is that if C evolves according to the periodic total flow, then its flow K matrix L of C evolves according to the periodic total flow on L of C, which I introduced in the previous slide. And so the first fact about the evolution on L of C is that it's a Hamiltonian system on the coadjoint orbits of some loop group G tilde in this set. Okay, so I call this set T, K, K prime. We can also identify such coadjoint orbits with those of a finite-dimensional Lie group, which appears in the form of a semi-direct product, which I'm going to show you. Okay, so some further notations. So the Lie algebras, we have Lie algebras G, N plus or minus, and B plus or minus. I'm going to denote by corresponding capital letters the simply connected Lie groups that integrate these Lie algebras. Introduce a loop group L, G, and so also introduce some Lie subgroups of LG. So the first one is LG plus. Second one is LG minus. So LG plus consists of loops which extend analytically to the interior of the unit circle. And LG minus is, consists of loops which extend analytically to the exterior of the unit circle. Okay, then we have further subgroups. So we have N minus tilde, which consists of loops in LG minus, subject to the condition that the value at infinity is in N minus. Similarly, there's a B plus tilde, which consists of loops in the LG plus, and the value at 0 is in B plus. So these are the Lie subgroups of LG plus and minus, which I'm going to work with. Okay, so now with these two Lie subgroups in equation 12, I'm going to introduce G tilde. So G tilde consists of loops in LG, which can be factorized into G plus times, this does not seem to work. Okay, so G can be factorized into G plus times G minus inverse. So G plus is in B plus tilde, and G minus is in N minus tilde. So we're going to endow this G tilde with a Lie group structure given by multiplication in this equation 14. So all this is quite standard in the R matrix, so-called R matrix theory. Okay, so now I'm going to introduce some coordinate functions introduced by corresponding to the boundary elements of L0, L minus 1, and L1 for L in T, K, K prime. Okay, so there are two sets of quantities in which the number K appears. And there are another set of quantities in which K prime appears. Okay, so the basic result here is that the set which I call T, K, K prime, this is invariant under the coadjoint action of this loop group G tilde. And the Lax equation of the periodic total flow, so this is the one for L. This is Hamiltonian on the coadjoint orbits of this loop group. in T, K, K prime with a quadratic Hamiltonian. So the parenthesis LG here is just a pairing on the loop algebra. So you take the trace of L square, right? Divide by 2 pi IC, and you integrate over some small contour center at the origin. So that's the pairing. Okay, so so that tells us that we're dealing with Hamiltonian equations on coadjoint orbits of some loop group. And so the coordinate functions corresponding to the boundary elements of the loops. So the functions corresponding to K prime, these are invariant under the coadjoint action of the loop group G tilde. And the ones in which a K appear, these are semi-invariants. Okay, so now we introduce two functions, P of L and also P prime of L. So the point here is that all the boundary entries are non-zero. Okay, and then I'm going to introduce further quantities. So this is already in Moerbeke and Mumford. So there are quantities which I call sigma I, and there are quantities which I call sigma I prime. So these quantities, they are formed from the coordinate functions corresponding to the boundary elements. Okay, so I'm pulling these things out from thin air, but they actually arise very naturally when they analyze the nature of the spectral curve. Now, but for me, I will these quantities will have some special meaning. Okay. So another result. So the set G prime so consists of loops for which all the boundary entries are non-zero. So this set is an open dense subset of TK K prime, which is invariant under the coadjoint action of the loop group G tilde. The functions sigma I and sigma I prime, these quantities, they are all invariant under the coadjoint action of the loop group G tilde. Okay, so from this result, we're going to look at the set G. So G consists of loops in G prime for which the sigma i's are all distinct, the sigma I primes are all distinct. Okay, so in fact, the corresponding set, that's what Moerbeke and Mumford call a set of regular periodic difference operators. Okay, so that's what they mean by regularity. Now, so for me, this has a special meaning. So this set, because of the result up there, this is an open dense subset of TKK prime, invariant under the coadjoint action of G tilde. Okay, so now I'm going to define what I mean by generic. So a loop in this TKK prime is generic if and only if L belongs to this set G. And a coadjoint orbit through L is generic if and only if the loop L is generic. So that's what I mean by generic. Okay, so now I'm going to discuss the generic coadjoint orbits, and I will calculate the dimension of the generic orbits, and that will give me the phase spaces of my systems. Okay, so the theorem is that the dimension of the generic coadjoint orbits of G tilde in G is given by this magic number. So that's equal to n minus 1 times the sum of k and k prime plus d prime minus d. Okay, so let me say something about the proof. Also show you the semi-direct product group, which I mentioned earlier. So the proof doesn't make use of the standard fact that coadjoint orbits are homogeneous spaces. Now, however, I cannot work with the loop group, right? Because the loop group is infinite dimensional. So turns out that the coadjoint orbits also come from a finite dimensional Lie group, which I call S. And so the approach here is to compute the dimension of the isoptropy subalgebra through a generic element, and this is where the knowledge of S is very important. Okay, so this is the form of S. So, okay, so it's a semi-direct product. So there's a group which I call G sub J. So G sub J is essentially the Lie group corresponding to the J bracket, which I mentioned earlier. Yeah, so the Gj as a submanifold is given by the set here. And this is the multiplication operation on G sub J. And so G sub J acts on the direct sum of G with itself, and the action is given by this formula here. Okay, so B acts on Kasi and eta, so the first component is add B plus of Kasi, second component is add B minus of eta. Okay, so that's the idea of the proof. And so this is the first step, right? So I know that the generic phase spaces have this dimension. Okay, so the next thing to do is to count the number of non-trivial integrals in involution. So because we have an isospectral flow on L of C, so if you write down the characteristic polynomial and make an expansion, all the coefficients will give you integrals. And furthermore, they will be in involution because of an abstract theorem in the group theoretic scheme. Yeah, so here I expand, and then I obtain the coefficients, which I denote by IRJ. Okay, so all these coefficients are conserved quantities of the periodic total flow. However, some of these conserved quantities actually Casimirs or coadjoint of the invariance. So I have to separate out these coadjoint of the invariance from the non-trivial integrals. And that turns out to be a quite delicate business. Okay, so here, the Casimirs or coadjoint of the invariance will come from the top and bottom coefficients in this expansion in equation 24. But not everything are Casimirs. So it turns out that to pick out the Casimirs, you need to introduce two sets here, which I call E and E prime. Okay, so E and E prime are defined in equation 23. And so E, if I look at E, is characterized by some arithmetic conditions. So the square bracket is the greatest integer function or floor function. M sub R is the exponent of the Lie algebra. In this case, the Lie algebra is just GLNC. The exponent is given by R, and D sub R is M sub R plus 1. And the quantity H is the so-called Coxeter number, and in this case, it's equal to N. Okay, so all these things are naturally generalized to the general case of a simple Lie algebra. Okay? So the result is this. The result is that if R is in E, then the corresponding top coefficient is a Casimir. And if R is in E prime, then the corresponding bottom coefficient is also a Casimir. And the others are not Casimirs. Okay, so after separating out the Casimirs from the non-trivial integrals in involution, we can now compute this number. So the number of non-trivial RJs in involution is given by this number here. And this is exactly 1/2 the dimension of the generic coadjoint office in TK K prime. Okay, so of course we still have to show the functional independence of the non-trivial integrals, and so we'll do this by constructing angle type variables, which are also relevant in improving on the dictionary mentioned in the beginning. Okay, so now I'm going to modify the spectral curve a little bit because I don't want to deal with 1 over c, so I multiply L of c by c. So I'm going to call the characteristic polynomial by I. So that turns out to have some advantage because it means that I can put the Newton polygon in the first quadrant. Okay, so the equation, of course, I equal to 0 defines an applied curve. I'm going to embed this curve in a weighted projective space. So in this case, it's P2, 1, 1, 2. And I will denote the closure by C of L. And then for generic choice of L, this C of L is irreducible. It has singular points only at 2 points. One point is P0. The other point is P infinity, it's a point at infinity. And so both singular points are non-ordinary singular points. Okay, so now I have these two results. First of all, the genus of the non-singular model C tilde of L, of C of L, is given by this number here in equation 27. And a basis of holomorphic one-forms of this C tilde of L is given by the quantities here. Yeah, for some reason. Yeah, here. So these are the holomorphic one-form. Now, so here, the pair AB is in lattice points in the interior of delta I. So delta I is the Newton polygon associated with this polynomial I. So here actually I'm using a result due to Kowalski. Yeah. So this is actually a special case of a wonderful result of Kowalski. So of course, the result doesn't come for free. And you do have to check something. So here the thing to check is that for generic L, the polynomial I, which depends on L, is non-degenerate with respect to the Newton polygon, delta of I. And so in this case, what is nice is that we can show that this delta of I is a very simple region. It's just a triangular region with vertices at 3 points, so 0, n minus k 0, n plus k prime 0. Okay, so I believe if I had worked with the other curve with the 1 over c, I may not be able to identify the Newton polygon. So in this case, because I have moved the Newton polygon to the first quadrant, I can easily identify that. Okay, so now denote by phi the normalization of this embedded curve C of L. Then over the singular point P0, there are D points, and over the singular point P infinity, there are D prime points. Okay, so notice that the number of non-trivial integrals, ILJ, minus the genus of this normalization is equal to D prime. It's the number D prime minus 1. So if D prime is not equal to 1, you will see this will have some serious repercussions. Okay, so here I'm going to make use of a result of Moerbeke and Mumford. They have studied the divisor very carefully. Okay, so introduce the eigenvector, which is denoted by F bar here. The last component is given by C. Then there exists n regular divisors with genus equal to G. With degree equal to the genus, such that the divisor of the Fi has this structure here in equation 30. And I'm going to denote by D of L, the divisor Dn of L. Okay, so here the P0 of A, P infinity A have been extended by periodicity. Okay, so for L in G satisfying some additional genericity assumptions, we define these quantities VAB of L. So we integrate the omega AB, the holomorphic one forms, on the normalization from some fixed divisor to this divisor D of L. Okay, then we have this result. We have the for AB in for lattice points AB in the interior of the Newton polygon, and for J between these two numbers, we have this Poisson bracket relations. Poisson bracket of VAB with IRJ is given by this simple quantity on the right-hand side. So here we have to discuss we have to divide into two cases. If D prime is equal to 1, then the number of non-trivial integrals in involution is exactly equal to the genus of the curve. So in this case, this theorem, D1, will imply functional independence of the integrals, and Liouville integrability follows. However, in a case when D prime is greater than 1, then in this case, there exist quantities which don't move on the Jacobi variety. So these quantities, I n1 prime mu minus k1 prime mu. So the Hamiltonian flows generated by these quantities, they don't move on the Jacobi variety. So that means we need to find variables that move linearly under the Hamiltonian flows generated by these quantities. Okay, so here instead of working directly with the i's, it's actually more convenient to work with an equivalent set of variables which are related to the I. So these quantities I call Ji infinity. And so the quantities that move linearly by the corresponding Hamiltonian flows are associated with the points P infinity 1, P infinity prime. So these are points lying over the singular point P infinity. Okay, so here I introduce a normalized eigenvector which I call V hat. So this is an eigenvector normalized so that the last component is equal to 1. Okay, so the important fact here is that this eigenvector V hat evaluated at P infinity I, this quantity exists, and in fact is an eigenvector of the lower triangular matrix given by the evaluation of this quantity. So L C of P raised to the n1 prime times C of P raised to the minus k1 prime evaluated at P infinity I. So this quantity, this matrix is a lower triangular matrix. Okay, and then you have these Poisson bracket relations. So here we are just making use of the n minus d prime plus ith component of V hat evaluated at P infinity I. Yeah, so we have these Poisson bracket relations. So here the capital A is just the loop evaluated at C equal to 1. And if we combine theorem D1 with this theorem D2, then we can deduce Liouville integrability in case 2. Okay, so now I'm getting into the last part. Okay, so now I'm trying to improve the dictionary in Moerbeke and Mumford, right? So here, there's a map that takes L to a collection of data. So on the right-hand side of the spectral curve, C of L, with normalization, I have the divisor, which I call D of L. And then I have these quantities that come from V hat. And in addition, I have some boundary elements. So remember, some of the boundary elements are coadjoint of the invariance. So I put in those boundary elements. Okay, so the result is that this is a bijection from some subset, which I denote by tau star kk prime, onto some subset D, which I call the set of admissible extended algebro-geometric data. So the T star kk prime is some open subset T kk prime defined by a collection of genericity assumptions. And then we can obtain a complete characterization of this subset D, which I'm not going to show, but it's an important part of the inverse problem. Okay, so this is something, a collection of genericity assumptions that characterized the set tau star kk prime. Yeah, it's quite a list here. Okay, so I'm going to stop here. And happy birthday, Carlos.
Thank you, Luen-Chau. There's time for some questions.
Well, I have a million questions.
Carlos.
But it's almost embarrassing to come up with a question after such a massive piece of work. Luen-Chau and I have been working together for such a long time, and I'm impressed by the fact that whenever he starts something, I feel like, oh, this is not going to work. And eventually, he makes his magic and things happen. And it happened again, right? That you were able to combine the loop stuff with the periodic.
Yeah, so, when June gave me the paper, it was just very hard. And I was only able to go through the first couple of pages. And then I put it aside. So it was in my file cabinet for many years, right?
Amazing.
Yeah, and then a friend dropped by. He told me about the work of Penn at Liouville, and at that time, I didn't even know that had some connection, right? So.
Amazing. But I want to make just the smallest possible question, right? When you build the S, the finite-dimensional Lie group, right? I was expecting you to get it from quotients of the kind, the coadjoint orbit is really associated to very few degrees of Z on the left and on the right, right? Pretty much like the paper we wrote for Percy, right? And you came up with a different trick, right?
Yeah, so yeah. I mean, because the orbits I'm dealing with are finite dimensional orbits, right? So there ought to be some finite dimensional group involved. And you have to take into account the structure of the coefficients, the L0, L1, and the free term that defines the L of C,
But you think you could have taken the road we took in that other paper of ours. Would that be possible?
No, that won't be possible. But the best way, I'm not doing it in the best way possible, I can tell you. So that's my confession, right? So because in this way of doing things, you don't really know all the coadjoint orbit invariants. Yeah, the only way to know all the coadjoint orbit invariants is to find a normal form for the, so starting from the expression for the coadjoint action, find a normal form for the, of the expression, right? So in fact, that's what I did in the problem with Xiaohu. So because Xiaohu was very good in doing some simulations, so he was able to guess at a normal form. So and then we can prove it. Yeah. So in this case, I'm not trying to do that. Yeah. Yeah, that would be the best way you can have the whole set of coadjoint orbit invariants. Yeah. Now, but there are coadjoint orbit invariants that are not on the curve, which are not associated with curve, right? So some of those are given by the boundary elements, right? Yeah.
Amazing stuff.
Any other questions? Yeah.
Maybe I have a silly question, but would it be possible to apply these techniques to other Lie algebra decompositions? So,
in fact, I have some partial results, and that's why I was able to tell you the top and bottom coefficients of that polynomial can be expressed in terms of, say, KdR divided by H, greatest integer function. So those things also work for any complex simple Lie algebra, right? And so in that case, you have Kostant-Toda number and exponent plus 1. And so those things can be generalized. Yeah. Yeah, but you won't be able to build the angle variables in this way. So.
Can you talk a little bit about applications like in physics or numerical analysis?
No, I don't really have any applications in mind when I am doing this. No, I don't have any applications. Yeah. The total lattice, of course, has many applications, right? But this is a generalization. And yeah, but yeah. So no, I don't really know any applications.
Well, here we are.
I have one question. Before you embark on proving that the system is completely integrable, do you know if it's going to have singularities that form? Or is it always clear it's going to be global existence will work?
Yeah. Are you talking about the singularity of the curve or the
In time.
in time? Oh, no. I think these things will blow up. Yeah. Yeah, this will blow up. Yeah, it's just like LU and also Cholesky, right? We know that things can blow up in finite time. And so what happens to the divisor, right? There's nothing wrong with the divisor. It's just that map doesn't work, right? Yeah. Yeah, yes, these things will blow up. Yeah.
So I have a question about the quadrant structure. So you regard the quadrant orbits as the quadrant orbits of the infinite-dimensional group at the very beginning.
Yeah.
But then when you introduce the group S,
Yeah.
so it also comes with its own linear, with its own quadrant structure. So are these two related? So the symplectic structure that you put in the finite-dimensional.
Oh, yeah, I think there are some relations because the two sets of orbits coadjointly coincide, right? So, yeah, now this is something I haven't checked, but I believe that the finite-dimensional subgroup should be sitting inside the bigger one. Yeah, sitting inside the bigger one. Yeah, yeah. Yeah, because in building the bigger one, I do have to make use of the fact that my Lie algebra can be decomposed in a direct sum of B plus and N minus, right? So that's how I build the J, right? Yeah. Yeah. Should be related. But I haven't checked it yet.
Okay. So, if there's no further questions, Luen-Chau, thank you so much.
Yeah, thank you. Thank you.
And according to the schedule, we have some coffee.
That's understandable.
That's easy.